Hi everyone, I'm Dan Fullerton and I'd like to welcome you back to educator.com. Today we're going to continue our study of fluids as we talk about pressure and Pascal's principle. So our objectives are going to be to calculate pressure as the force a system exerts over an area, to explain the difference between gauge pressure and absolute pressure, and explain the operation of a hydraulic system as a function of equal pressure spread throughout a fluid. So pressure. Pressure is the effect of a force acting upon a surface. It's a scalar, it's a force per unit area, and its units are newtons per meter squared, which are also known as pascals, which we typically abbreviate capital P little a. So if pressure is force per unit area, our formula for pressure, P equals F over A. Now it's important to note that the force is always perpendicular to the surface it's acting on. So, exerting pressure. All states of matter can exert pressure. When you walk across an ice-covered lake, you exert pressure on the ice equal to your weight divided by the area which contacts the ice. That's why, if you don't want to crack the ice, they teach you to spread your hands and feet out, to spread out that force over a larger area so you get less pressure. Walk on snow with snowshoes with large areas of contact. As you increase the area, you reduce the pressure and you walk on top of the snow. That's why they're so big, larger area. Now, fluids exert outward pressure in all directions on the sides of any container holding the fluid. Even Earth's atmosphere exerts pressure. Atmospheric pressure is about 101,325 pascals, which will typically round to about 100,000 pascals, or 10 newtons per centimeter squared. And you can even experience this by riding in an airplane. As you change altitudes, go up and down, you may experience a popping sensation in your ears. The pressure inside your ear balances the pressure outside your ear in a transfer of air through some small tubes connecting your inner ear to your throat. When that happens, you hear that or feel that popping sensation. Let's take a look at our first example, pressure on a keyboard. Air pressure is approximately 100,000 pascals. What force is exerted on your keyboard when it is sitting flat on a desk if the area of the keyboard is 0.035 square meters? Well, if pressure is force divided by area, then that means force is pressure times area. If our pressure is about 100,000 pascals times our area of 0.035 square meters, that will give us a force of about 3,500 newtons. Let's take a look at the example of a sleepy fisherman. A fisherman with a mass of 75 kilograms falls asleep on his four-legged chair of mass 5 kilograms. If each leg of the chair has a surface area of 2.5 times 10 to the minus 4 square meters in contact with the ground, what's the average pressure exerted by the fisherman and chair on the ground? Well, the force applied is going to be the force of gravity. So our pressure is going to be force over area, which is going to be mg divided by A. Now our mass is 75 kilograms the fisherman plus 5 kilograms for the chair times g, about 10 meters per second squared, all over the area, which is going to be the four corners of the chair, the four legs of the chair, times the area of each leg, 2.5 times 10 to the minus 4 square meters, or about 800,000 pascals. Let's take a look at another one. A scale which reads 0 in the vacuum of space is placed on the surface of planet Physica. On the planet's surface, the scale indicates a force of 10,000 newtons. Calculate the surface area of the scale, given that atmospheric pressure on the surface of Physica is 80,000 pascals. If pressure is force over area, then area is force over pressure. That'll be 10,000 newtons over our pressure of 80,000 pascals, or about 0.125 square meters. Let's see if we can't rank some pressures. Rank the following from highest pressure to lowest pressure upon the ground. The atmosphere at sea level. Well, that we know is right around 100,000 pascals. A 7,000 kilogram elephant with total area 0.5 square meter in contact with the ground. Well, pressure will be force over area, or that'll be 7,000 kilograms times G, 10, over the area of 0.5, or about 140,000 pascals. A 65 kilogram lady in high heels with the total area 0.005 square meters in contact with the ground. Pressure is force over area. That'll be 65 kilograms times 10 meters per second squared all over our area of 0.005, or about 130,000 pascals. And finally, a 1,600 kilogram car with the total tire contact area of 0.2 square meters. Pressure equals force over area. It'll be 1,600 kilograms times 10 meters per second squared over 0.2 square meters, or about 80,000 pascals. So if I were to rank these from highest pressure to lowest pressure, I'd start with the elephant, B, go to the lady in high heels, atmospheric pressure, and finally the car. So B, C, A, D. Let's talk about pressure on a submerged object. The pressure a fluid exerts on an object submerged in that fluid is determined by multiplying the density of the fluid by the depth submerged, all multiplied by the acceleration due to gravity. We call that the gauge pressure is rho density times G times H. If there is also atmosphere above the fluid, such as the situation here on Earth, you can determine the absolute or total pressure by adding in the atmospheric pressure, which we'll write as P0, which is about 100,000 pascals. So absolute pressure is atmospheric pressure plus gauge pressure, P0 plus rho, where rho is the density of the fluid, GH. Let's take an example of gauge pressure. Samantha spots buried treasure while scuba diving on her Caribbean vacation. If she must descend to a depth of 40 meters to examine the treasure, what gauge pressure will she read on her scuba equipment? The density of seawater is 1025 kilograms per meter cubed. Well, we want gauge pressure, so that's going to be rho fluid GH, or 1025 kilograms per cubic meter times G, 10 meters per second squared, times her depth of 40 meters, or about 410,000 pascals. If we want to look at absolute pressure here, let's find the absolute pressure for Samantha in the same scenario. Now we're looking for absolute pressure. That's P0 plus gauge pressure. And we're going to say atmospheric pressure is about 100,000 pascals for simplicity. So 100,000 plus the gauge pressure we just determined was 410,000 pascals, for a total of about 510,000 pascals of pressure as the absolute pressure. So let's talk about Pascal's principle. When a force is applied to a contained incompressible fluid, the pressure increases equally in all directions throughout that fluid. This is the foundation for hydraulic systems in things like barbershop chairs, construction equipment, and even car brakes. In car brakes in the movies, you'll even sometimes see people cut the brake lines so the brakes don't work. The fluid leaks out and the brakes no longer work because the fluid is no longer contained. It must be a contained fluid and incompressible or nearly incompressible fluid. So let's talk about force multiplication using Pascal's principle, also known as the basis of hydraulics. To begin with, we have a force F1 that we're applying to a piston of area A1, and that's going to create a pressure P1. So pressure 1 is caused by force F1 applied to a piston of area A1 on a contained incompressible fluid. We've got a closed container incompressible fluid here. Now over on the right-hand side, the pressure on this piston must be F2 over A2. Why? By Pascal's principle, you must have the same pressure anywhere throughout the fluid. Well, when you do that, let's take a look at the ramifications. If P1 equals P2, by Pascal's principle, then that means F1 over A1 must equal F2 over A2. Or, if I cross multiply, F1A2 equals F2A1, or F2 by itself, F2 is equal to A2 over A1 times F1. What does this mean? You have increased the force. If you apply a force F1 and you have a different area on your two pistons, you can increase that force by the ratio of the areas. If area 2 is 5 times larger than area 1, you applied force F1, you get 5 times that force on F2. You've effectively increased your applied force. Now, you don't really get anything for free here. What you're going to end up having by conservation of energy is you're also going to have to push this piston 5 times further, or you'll get 1/5 the displacement that you would over here for the same displacement over there. The total work done on each side has to be the same for conservation of energy. And that's going to be by the same ratio as the area multiplier. But you can multiply a force. If the areas are a ratio of 100 to 1, you've increased your force by a factor of 100. That's the principle behind hydraulic systems. So let's take the example of a barber's chair when we apply this. A barber raises his customer's chair by applying a force of 150 newtons to a hydraulic piston of area 0.01 square meter. If the chair is attached to a piston of area 0.1 square meter, how massive a customer can the chair raise? Assume the chair itself has a mass of 5 kilograms. Well, to solve this problem, let's first determine the force applied to the larger piston. We know F2 must be equal to the ratio of the areas A2 over A1 times F1. Therefore, F2 will equal 0.1 A2 divided by 0.01 A1. That's going to be 10 times F1, 150 newtons, or 1,500 newtons. This is the largest applied force you can have. Now then, if we want to know how massive a customer the chair can raise, if our force is 1,500 newtons, that must be equal to the weight. That's the maximum that we can handle. Therefore, the mass that you can handle is 1,500 newtons over g, which is 10 meters per second squared, or 150 kilograms. Now, of that 150 kilograms, 5 of those kilograms have to be the chair. Therefore, you could lift a customer of 145 kilograms, about 300 pounds. Let's take a look at the hydraulic auto lift. A hydraulic system is used to lift a 2,000 kilogram vehicle in an auto garage. If the vehicle sits on a piston of area half a square meter and a force is applied to the piston of area 0.03 square meters, what is the minimum force that must be applied to lift the vehicle? Well, starting with Pascal's principle, we know that P1 is going to be equal to P2, assuming we have a contained incompressible fluid. Therefore, F1 over A1 must equal F2 over A2. And we're looking for F1, so that's going to be A1 over A2 times F2, which is 0.03 square meters over 0.5 square meters, times F2 is going to be the weight of our vehicle, 2,000 kilograms, times the acceleration due to gravity, 10. Therefore, F1 must be 1,200 newtons. Have to be able to apply 1,200 newtons in order to lift that 20,000 newton vehicle. Let's take a look at the pressure on a penny. A penny with a diameter of 19.05 millimeters sits on the bottom of the ocean where we have a saltwater density of 1025 kilograms per meter cubed at a depth of 340 meters. What is the force on the penny? Let's figure out the area of the penny first. the area for the penny is pi r squared. So that's going to be pi. And the radius of the penny will be half the diameter, or half of 19.05 millimeters. That's 0.009525 meters squared, or about 2.85 times 10 to the minus 4 square meters. Now, if we're looking for the force on the penny, let's start by finding the pressure. The absolute pressure is the atmospheric pressure plus the gauge pressure, rho gh. So that'll be about 100,000 pascals, plus our density of our fluid, 1025, the acceleration due to gravity, 10 meters per second squared, and our depth, 340 meters, or about 3,585,000 pascals. Now to find the force, if pressure equals force over area, then that means force equals pressure times area, or 3,585,000 pascals times our area of 2.85 times 10 to the minus 4 square meters, for a force of about 1,022 newtons. Quite a force on a little penny. How about depth in freshwater? A diver's pressure gauge reads 250,000 pascals in fresh water. How deep is the diver? Well, pressure, gauge pressure, is rho gh. Therefore, h is pressure over rho g, or 250,000 pascals over 1,000 kilograms per meter cubed, our density of fresh water, times g, 10, or 25 meters. One more. A pressure gauge reads 350,000 pascals. What's the absolute pressure? Well, just to review, absolute pressure is atmospheric pressure plus rho g h, or 100,000 pascals atmospheric pressure plus the gauge pressure, 350,000 pascals, for a total absolute pressure of about 450,000 pascals. All right, hopefully that gets you a great start with pressure in Pascal's principle. Thank you so much for your time and for watching us on educator.com. Looking forward to seeing you again, and make it a great day.